Today we're going to talk about, based on what we talked about last time, we're going to talk about conservation laws, simple harmonic oscillators, and then we're going to talk a little bit about continuum mechanics using the example of a string, and then a brief review of linear algebra. Okay. So previously we defined what is a Lagrangian. It is the difference between the kinetic and the potential energies of the system. And then we also told you that in the Lagrangian mechanics, the action and the principle of least action is what guides the composition of writing down the equations of motion. And the Euler-Lagrange equation for each degree of freedom is given by this. Okay. So now today, so I'm going to start by talking about a conservation law, and that is the conservation of energy. So let's consider a Lagrangian. No explicit time dimension. So I want to stress that the Lagrangian, of course, is going to be time dependent in general, because as your system evolves, the difference between the kinetic and potential energy are going to be a function of time. But explicit time dependence means that it's not dependent on time through the position or the velocity. There's an explicit function of time. And that corresponds to when your potential function is an explicit function of time. So let's consider no explicit time dependence. Then let's consider the total time derivative of the Lagrangian. Okay, and since there's no time dependence, we're going to just have this. And I'll explain this notation further because there was some confusion from last time. Okay, so what do I mean when I say there's a summation over the index I? I mean that each of these indexes one degree of freedom of the system. So we could have a one particle Lagrangian, and these degrees of freedom will correspond to the x, y, and z coordinates of that particle. And then maybe we can have multiple particles. But in general, if we have n particles, and say there's no constraint in the motion of the particles, then the degrees of freedom is going to be 3n. Okay, and the summation over I is summing over all of the degrees of freedom of the system. So you would have a linear summation for each degree of freedom, and this equation in turn specifies how that degree of freedom is going to evolve in time, and that's how you solve for the system. Okay. So now. This is true for any Lagrangian that has no explicit time dependence. But now let's use the Euler-Lagrange equation and replace this part. Because the Euler-Lagrange equation says that this is equal to the time derivative of this. Okay. Okay, so now having plugged in the Euler-Lagrange equation, we're restricting our discussion to the path and to the paths that satisfy the equations of motion. Okay, and you'll see from here that you should be sensitive about these terms. You see that there's a time derivative of this term here, and then there's a time derivative of this term here. Okay, and let me just replace this by qi naught. So that you see. Now these two terms can combine using chain rule. Okay? And we can combine them into the total time derivative of the product. As you can easily verify by going from here to here. Okay. So now what this says is we have we have reproduced a total time derivative on the right-hand side as well. So if I now move this across, or move the Lagrangian to this side, what we will get is, okay. So now you see that the motion has a conserved quantity, meaning that that quantity's time derivative is 0. Okay. And this is only true if we plug in the Euler-Lagrange equation. So that means for the path that the system evolves in, there's a conserved quantity. Okay. And per our definition of the generalized momenta, so last time we defined this. Okay, so if you plug this in, you recognize that this is just what we define to be the Hamiltonian of the system. Okay. So the conservation law here is that if we have a system that with the potential function not explicitly dependent on time, then that is called a closed system. And for a closed system, the Hamiltonian, or the total energy of the system, is a constant of motion. Okay. So you can say that in a way, since we use the Euler-Lagrange equations in here to derive this constant of motion, you can say that the requirement that the total energy should be a constant for a closed system is equivalent to the principle of least action. So the motion of a particle in classical mechanics is guided in some sense by the principle of least action, but it's also guided by conservation of energy. Okay. So this is the point I wanted to stress, and this gives the physical meaning of the Hamiltonian more clearly. Okay. So next, we're going to move on to talk about the simple harmonic oscillator, and let's do the simple harmonic oscillator from the. So yeah, okay. So is there any questions regarding this one?
So is Hamiltonian always so that you always give the Hamiltonian that we express a Lagrangian as a time derivative or something?
What do you mean?
Is a Hamiltonian always of that form?
Yeah, this is the definition of the Hamiltonian. Are there any other questions regarding this point?
Why do you also say that Hamiltonian is often written as T plus V? It's like you said last time. So that can be cast into that form.
Okay. Yeah, so remember that the Lagrangian is equal to T minus V. And then you can see that for most the kinetic energy is going to be dependent on the square of velocities. So if I take the derivative with respect to the velocity here, I'm going to get that two factor out, and that's going to be twice the kinetic energy in general. So twice the kinetic energy minus T minus V turns into T plus V, right? And that is the total energy of the system. So one thing I did not clarify was last time we wrote the dependence of T. In general, T can depend on coordinate and velocity. But when does T depend on the coordinate? Can you guys think of an example? So we all know that it's a half mv squared, this kind of dependence, right? But when does the coordinate comes in to the kinetic energy? It's when we have rotation. Right? Okay. And the good thing, and the other good thing about the Lagrange equation is that notice that in the equation of motion, we're going to take derivative of the Lagrangian with respect to the coordinate. Now, if you have rotation in the system, what does that? That's going to be picked up by this derivative. Okay, and those are the forces, like centripetal force and centrifugal force, that in Newtonian mechanics you would have to treat specially, because those are forces coming from having a non-inertial frame. Okay. But in Lagrangian mechanics, they fall out of the Lagrangian very naturally. Okay, so this is one more advantage of the Lagrangian formula. Okay. Are there any questions? Alright, so now I'd like to move on to a simple harmonic oscillator. And for that, let's consider the simplest picture of a mass m, now restrained to moving in one dimension, and then it's connected to through a spring to a wall. Okay. And we can easily write down the Lagrangian for this system. It's going to be composed of the kinetic energy of the mass, which is given by 1/2 mv squared. And let's put everything in terms of a coordinate. So that coordinate is going to be this, the distance here, which is x. Okay. So that is going to be 1/2 x dot squared. And then the kinetic energy, so this is what we're defining the Lagrangian. The kinetic energy with a minus sign. It's going to be the kinetic energy of the spring. And that is going to be 1/2 k. Now the last term is you need to take some care here because the spring, the compressive energy stored in the spring is dependent on the change in the spring from its rest length. So it's going to be delta x squared. So it makes sense for us to define the coordinate system so that the length is referenced to its rest to the spring's uncompressed length. Okay, and in that case, let's say that maybe the zero of the axis starts here. Okay, then my x is defined relative to this axis, and that does not affect the time derivative of x. But now we can conveniently write this as 1/2 kx squared. So this is the Lagrangian of simple harmonic oscillator, and it's quite simple to construct this Lagrangian. This is very elementary. So let's derive the equation of motion using the Euler-Lagrange equation here. Okay. So it says that we should first take the spatial derivative with respect to the coordinate x. Okay, and that will give you minus kx. And then the next term on the other side is going to be the time derivative of the velocity derivative of the Lagrangian, which gives you mx dot. Okay, so what this says is that mx double dot is equal to minus kx. And this, you should be familiar from Hamiltonian mechanics, is the equation governing the simple harmonic oscillator. And you know that this is going to, because of this minus sign here, it's going to admit solutions that are sinusoidal, or you can use complex exponentials. We're not going to cover that, but
Ian, what you mentioned that q becomes x. So
oh, okay.
Students can
So
just to change notation.
Yeah, sorry. Since I changed notation now, the coordinate q in this case is x, and the velocity is the time derivative of x. Okay. So this is a very simple example, but actually much physics can be gained by studying the simple harmonic oscillator. So let me just look ahead into the course and tell you why is it important that we study the simple harmonic oscillator. Because a lot of the models in physics are based on simple harmonic oscillator. For instance, I'm going to tell you about the what's called the semi-classical model of solids. Okay, so you probably know that the formation of solids, you can have two reasons for the formation of solids. Now, for solids that are formed from compounds that have one atom being very electronegative and the other one less electronegative, you would have an ionic solid. Right? And in that case, you can form a completely classical picture where you sum up. So, and if I draw a sketch of an ionic crystal, it will look something like this. Okay. Now these are the atomic sites, and the positive and negative ions are going to be in the middle of each other. Okay. So now you can find out what is the potential seen by this atom being a positive charge in the overall potential of all of its neighbors, and it's going to be in the form of a sum. Okay, and that sum is going to give you a function that looks like this. Okay, and this is called sometimes this is called the 12-6 potential. Okay. And what does this mean? Well, this says that, say we choose this coordinate. Let this be x. Okay. Let this x be the atom's distance from one of its nearest neighbors. So say we could define this to be x. But the potential looks exactly the same in this direction as well. So we're taking a slice of it. Okay. So and then notice that there is a let me call this V for potential energy. Notice that there is a minimum for this potential, and that is the equilibrium point for the atom to be in the field of its nearest neighbors. Okay. So this distance, for instance, is going to give you the average atomic distance in a solid. All right. So now what's special about this potential is that now when you look at this potential, and if we're considering really, really small displacement of the solid, of the atom around the minimum, then it's going to be quadratic in the displacement. Right? So in that case, this is a simple harmonic oscillator. Now there's also another form of solid, and those are held together by covalent bonding. Right? So this is the ionic solid. But there's also the covalent bonding. Now this is a little more complicated. There is no classical.
Why did you mention the fact that one is quadratic? It connects back to the second term in L.
Oh, okay.
The L second term describes the potential, and it's a quadratic potential. So it makes a connection between this quadratic behavior and that L that we have written down on the board.
Okay. So if I draw the quadratic potential of a simple harmonic oscillator here, notice that for close to the minimum, the two coincide very well. So you can model this behavior with a simple harmonic model. Now there's also a different kind of bonding called the covalent bonding. There's no classical way to explain covalent bonding. And in the course, you will study how we can calculate the covalent bond between two atoms that are not so different in electronegativity. And the potential you calculate again takes this form, but it's not a simple power law. Okay, but it still looks like this. Okay. So once again, near the minimum, you can model this solid as composed of a bunch of harmonic oscillators. Okay. So this is one reason why we want to study the harmonic oscillator. Now let's take, based on this example, let's take a simple one-dimensional case. Okay. So the one-dimensional case would be a chain of atoms, and we're going to model it with masses connected to springs, and then connected to more masses. Okay, I'm not going to draw the whole thing. Okay. So now, let's write down the Lagrangian for this system. And let's say that the masses, let's only consider the transverse motion. Okay, so the masses are not free to move in the longitudinal direction. Okay, the longitudinal direction is a bit more complicated. Okay. So for each of the atoms, of course, the kinetic energy can be written as this. 1/2 m, and let's put a subscript a to denote the mass of one area.
What axis is this being from?
Okay, so this is, let me call the coordinate system in this way. Let this be the x-axis, and let this be the y-axis. Okay, so the atoms are only free to move in the y-axis. Okay. And we're only considering very small oscillations. so that even though this is not, this is not strictly a spring, but for small oscillation, it still behaves like this. Okay. So, and this is going to be the position, the y coordinate of each of the atoms. I'm going to label with y of x, and for this, let's say that the interatomic distance is a, and this labels the first atom. So the maybe the first atom is here. Okay, so here is 0, and then the nth atom is located at Na. Okay, so and then we sum over all of the atoms. Okay, this is the kinetic energy part. Now the potential energy part requires a little bit more care. It's still going to be a summation over the atoms, but for now, you see that this atom, okay, is only affected by its two nearest neighbors. Okay, and we're going to use the delta y, the coordinate for the harmonic oscillator. This is going to be defined by the difference between this atom and its nearest neighbor. Okay. So let's choose this to be pointing one way. N plus 1 alpha, okay, minus y and okay. And then let's say that the spring constants are all identical. So this is going to be k. So this establishes the Lagrangian of the chain of atoms. Okay. So now the next thing we would like to do is take a continuum limit. And by that I mean we consider the atoms as they get closer and closer together. Okay. So some will turn into an integral, but there's some, we need to take care of some units here. So let's do this carefully. So over here, because we want to turn the sum into an integral, what we need is an infinitesimal element, the A. So let's factor out an A. And let's divide that A into the mass. Okay, so that gives you some kind of a mass density. So for the first term, we can say okay. So everybody follow with this. And for the second term, well, you recognize over here we have this difference. Okay. So in the continuum limit, this difference will turn into a differentiation provided we divide by the infinitesimal distance here. Right. So let's do that. And let's just write it. Well, because we're doing this inside of a square, so we will have a squared on the outside. Of course, one of them is going to give you the dx for your integration. What does the other one do? Well, we can combine these two terms. Now think about what is the unit of the k, the spring constant. Okay. Anybody? Newton's per meter. Because the Lagrangian is a measure of the difference in energy, right? So this has joules. Joules is Newton meters. So K is Newton per meter.
You're missing a square on that equation, the second line.
Oh, sorry. Okay. So now, if we combine these two, that gives us some kind of a force. Okay. And for a string, of course, we would call that the tension T. Okay. So now we can safely take the continuum limit for A going to approaching 0. This will give you the density, the mass density. So now the sums turn into an integral. And then let's call the, okay, we have to abuse a notation here because we're going to use the length for L to stand for the length of the chain as well. Okay, so you need to distinguish this with the Lagrangian. I'm sorry about this. Now this mass density turns into the rho, okay, and then your Na the discrete index turns into the continuous index. Okay, and we're going to index that by x. And then minus, okay.
You're missing the other a you didn't account for.
This a?
No, the first term has a little a.
Oh, I'm going to write that out.
Oh, you're going to write
Yeah,
that.
factor that
Okay.
out. So, and then this Ka thing turns into a force, and that is the tension. Okay, and then over here you recognize this just gives you the differentiation of y with respect to x. So we're going to denote the differentiation with respect to x by a prime. Okay, and now of course both of these a factors here now turn into the infinitesimal element dx. Okay. So now this is the Lagrangian for a continuum, a string. Okay. And now what can we do with this? Let's derive an equation of motion for the string. And to do that, let's use the principle of least action directly instead of directly using this. Because now there's a complication. We have a derivative with respect to x. So the Lagrangian is dependent on not only t, but also this independent variable x. So let's write down the action. The action is nothing more than the time integral of the Lagrangian. Okay, so we're going to integrate from t1 to t2.
Can you explain where the t dependence come in the previous line?
Wait, did this depend?
No, there's a time dependence, right?
Oh,
T
the y
little
dot.
t.
Right, the y dot.
Okay.
What's that rho? What? The rho is the mass density of this string.
Okay.
Right, the linear mass density, as you can see from dimensional analysis here. Okay. So now this action is dependent on two independent variables, time and t and x. Okay. And so if we were doing, so in general, our y is going to, maybe I should write this more carefully, okay, so that you guys get a clearer picture. So let me write the dependence of y out. Okay. So it's going to be dependent on both x and t. And in the first term, I'm going to take the time derivative denoted by a dot. Okay. In the second term, I'm going to take the spatial derivative denoted by a prime. Okay, so this is the Lagrangian. Now, when we vary our coordinate y, we're going to have to vary both x and t. Okay. So let's do the variations here. And I'm going to do this in some detail because you guys will encounter a similar problem in your homework this week. Okay, so let's consider, okay, inside of the integral, okay, we can think of the x and t being at each point fixed. Okay, so these two are independent. So now the action is dependent on two things: the time derivative and the spatial derivative. So when we do the variation, we need to treat them as independent. Okay. So what we can do here is, first of all, take the derivative with respect to the y dot. Okay. That's going to give you rho y dot. Okay. And then the variation is the time variation here. So multiplied by the variation in y. Is everybody clear with this term? Okay. So now the second one is going to give you, we'll do the same thing but with respect to y prime. But now the variation is done in the x almost.
We need to go through the taking the derivation more carefully. Explain why y squared becomes that and so on.
Okay,
Go through some elaboration on it.
okay. So let's write down the explicit the explicit dependence of the Lagrangian. Okay. So over here, our Lagrangian is dependent on y prime. It's also dependent on y dot. And there's no other explicit dependence, right? So now when we do the variation, remember, what we're doing is taking the Taylor expansion of the Lagrangian after we do the variation. So you can imagine this. Now we change y to y plus some arbitrary function that I'll call delta y. And that this is dependent on x and t as well, because we need to vary in both directions. Okay. So now, y prime is going to change to y plus delta y prime.
Y prime.
Oh, sorry. Yeah, y prime. And y dot is going to change to y dot plus delta y dot. Right? So now all we do is still, we do a two-term Taylor expansion in both y and y prime for L. Okay? And of course, when you take the difference, the zeroth order term cancels, and we're left with the first order term. So what we need to do is think about what you do when you write down the Taylor expansion. You take the partial derivative with respect to the variable you're expanding to, okay, say the y prime thing, and then you multiply to first order. You multiply by the change you made to that thing. So this gives you the second term. Okay? As you can see, you take the partial derivative of L with respect to y prime. Okay. You get this. Right? And the same thing for the y dot. Okay, is everybody clear on this point now? Okay. So now, what do we need to do? Well, we have both an integral over x and an integral over t. Remember, we always want to factor out the arbitrary variation so that we can conclude about something that is multiplying to. Okay. So now we want to get the time derivative off of this term, and that can be done by performing the time derivative, the time integration. Okay. And we want to get the spatial derivative off of this term, and that can be done through doing this spatial integration. Okay. So just integration by parts. Okay, so let's do the time integration here, and let's switch the integration order here. Okay, so if I now integrate this with respect to time, then I would get an integrated out part, which is evaluated at the two endpoints in time. Okay. And then this is multiplied by, oh, sorry. This is the integrated L piece. And then the term that remains in the integral acquires a minus sign. Okay. And there will be a integration over t. And the integral is moved up onto the y. Okay. So this is for the first part. The second part is completely analogous, but because we had a minus sign in the beginning, right, we're going to change to a plus sign, and then also there's
avoid somewhere on the second form.
Which one?
Is something missing in the second form?
Yes. Okay. Now for the second one, is everybody clear with this line? Yeah, I think everything is correct. So for the second line, we're going to use the spatial integration. So let's leave the time integration out. And the spatial integral, the integrated out piece, has a minus sign because of the minus sign to begin with. Okay. And then because we're going to apply a minus sign for the part that we're going to remain in the integral, that becomes a plus sign. And that's going to be an integral over x. And double prime denotes differentiation with respect to x twice. Okay. So now what do we need to do? We need to impose the boundary condition. And for now, let's consider a string fixed at both ends. Okay. And the variation in phi, of course, vanishes because you need to match the boundary condition in pi. So this term goes away. And for a fixed string, this term will go away. But say if the string was not fixed, okay, say if we allow the string to be free in one end, then you would just keep that term in one of those terms. Right? So for now, let's do this. And then now both of the leftover terms involve a integration over t and x. Okay, so they can be combined. Let's write the time integration on the outside, and this is just convention. So we have, there's a minus sign here. Let's put the positive term in the front. And then everything is multiplied by